All right, audio check. We got text check. I see slides in the window. See a green light on the streamer. I've relocated to an office with fine Wi-Fi here. So I'm hoping we can avoid some of those glitchy issues that we have. I think somebody's out there. Let me drop over to this window and see what's going on. There we go. We got some viewers. All right, let's get after it. Today, we're going to talk about dictionaries and hash tables. So our photo legend on the first slide has a copy of the New Oxford Dictionary of English. And on the far side over there, you'll see a pan of hash on a table. That's quality humor right there. It's quality humor. So we'll start by first discussing the dictionary ADT. It cuts out every other second. I am like rock solid on KBs. Rock solid on KBs, 0 dropped frames. Anyone? Anyone? Bueller? Anybody else? Yeah, I'm like I said, I'm at like consistent, no yellows, no reds, just 2600, 2700 KB per second, 0%, 0 drop frames. Very smooth. Ah, nice. Well, today, it's not me, it's you. 480p, that sounds like an insult. What'd you call me? Yeah, I don't know. Like I said, I moved to the office to upgrade the Wi-Fi. Looks like my mic is set a little high. It seems to be jumping into the peak area. Check, check, yeah. The final is not cumulative. The final is like roughly cumulative. I mean, there's things that you learn in the first half that you need to know for the final, but the lectures that the content lectures that the questions are drawn from are only the second half lectures. So, I mean, there's not going to be any direct questions about, say, complexity, but if there's a question that you need to know something about complexity for just to make a decision, then that's kind of how you need to have understood things from the front half. But there's no questions directly related to any lectures in the first half of the semester. So only the lectures after the midterm, from here on, are going to be lectures that have content straight on the exam. Overtime complexity on the exam, it depends on how much that is important to the problem. Some problems are fairly trivial and the difficulty is getting it done in the right amount of time, and so those are a bit more expensive in terms of the cost for going over time complexity. But in general, if you've got a perfectly good solution that's just out of time complexity, I don't want to, ding you 50%. That's just basically saying, well, if your overall grade was 50% of what it could have been, then that's like a pure fail. So, on one particular problem, if you miss complexity and it's kind of just a part of the thing, maybe you'll get dinged the equivalent of a letter grade. You know what I mean? Like a 10% deal or a 15% deal. Somewhere around there. It depends on what's going on there. All right. We seem to be okay here. Everyone but Dr. P is streaming just fine. Today we're going to talk about the dictionary abstract data type. We'll look at containers that have key lookup. We call these things bucket-based data structures. Kind of keep things in the digital equivalent of a bucket. We'll do that through hashing, and there's a couple of different portions of hashing that we're going to look at today. We're going to look at hash functions and how those get calculated and why they're useful, and then also compression, which is going to be needed to make sure that anything we do fits in the place that we're putting it. Another very important part of hashing is collision resolution down here at the bottom, but it's not on today's lecture docket. So tomorrow's lecture, or I guess it would be next week's now, Monday, we'll be going into the collision resolution aspect of how hashing works. Now, to be clear about hashing, we're going to talk about it today extensively. We're going to go into it, look at how it gets done, the mathematical level, programming level, but you are not probably ever going to implement a hash table, except for on the lab. You're going to partially implement a simple hash table. But when it comes time to use a hash table, languages have those built in. So if you're used to writing things in Python and you've ever used what's known as a dictionary type or a dict type, that is a hash table. You can put anything in there as the key to pull your data out. In the STL, we've got the unordered map, which is a hash table. So those are things that we will be using in project 3 here, the unordered map. There's also the map, which is, the ordered map, if you will, but it's not called an ordered map. It's just called the map. And the map uses a binary search tree underneath there. So it's got a different time complexity than the unordered map. The unordered map uses a hash table like we're going to look at today, and that's what gives us our average case constant time access. So the dictionary abstract data type, of course, is like any other abstract data type. It's a discussion of what functions are available and what data they work on. In this case, we're going to call it a dictionary because it's got that feel where we give it something and it gives us something back. To be clear, we've already done something like this with just integers. When we look at ordinal indexing that we use on a vector, we give some key to a vector, say give me the first position thing, well, I'll pass you 0 and you'll pass me the thing back. So it's not unlike that, but we get a little bit more flexibility in what we use to look something up. So here, as we talk about the dictionary, we say that's a container of items, and now an item is a key value pair, because it's important that the key and the value stay together. If we just had the buckets and we said, well, this key points to that bucket over there, and then you went over to that bucket and pulled out whatever you had, some cases it would make it hard for us to get the right data. So rather than having the key over here and the data over there, the way that we do this is with these items, which is a key value pair, and we'll put the key and the item together. So we say, well, the key says we should go look over in that bucket. So then you get to the bucket and there's an item there, but you also look at the key and say, well, is this exactly the key I was looking for? Yes. And why that will be important is because of collisions. Later on, as we start trying to figure out when the math makes things a little bit unclear, we do have a way to resolve that, and that's what collision resolution does for us. But what that also does is occasionally it puts an item in a place that you didn't first think to look for it. So if you went to the first place that you thought to look for it and the only thing there was the data, you wouldn't realize that you didn't have the right key. So you can check the key and then confirm that this is the data you want. If you get to that place and the key there is not the one you're looking for, then you will have some other formula to find the next place to look. And this will take a little bit more time than normal, but you still are trying to do the thing that we always try to, we can always fall back on linear search. There's a bunch of things, I can look at them all till I get what I want. But we're trying to find something a little bit more efficient than just a linear search. So we will get some efficiency out of doing this hash table. And I got this going on, make that stop. So what we're going to do is these two basic operations. Insert, that's how I put something into the container, this dictionary, and search or retrieve, how do I get the value back that's associated with some key that I have been given. Two primary uses of dictionary types are using this to manage a set of things. And this is set in the mathematical sense where I have a collection of them. So I would like to see if something is in the set. Have I already seen something with that character? Have I already seen something with that string? Have I already seen something with some identifying piece? If I've already seen one, then I know that I've got it. Another one is to use this key value storage where we're actually doing something with the value there. So part of it is just being able to say, hey, does this exist? Can I find out whether it exists in a constant amount of time? Which is a non-trivial thing. If I've got a bunch of different items and say I've got 10,000 items and someone says, well, is this one of your items? How do I find that? If I go brute force, of course, I look at all 10,000 of them and I've found that I do have it or I don't. But I would like something a little bit speedier. So that's where this set checking aspect of it works. I've got a dictionary, I say, well, here's the key that I'm looking for. And it just goes and says, yes, that key exists here. And many times that's good enough for what you use a dictionary for. You don't really have to use the value, but it's nice to know in constant time if what you're looking for is a part of what you've got. The other version is, well, yeah, every time I go get that value, I might want to change it or read something from it to do something with it. So our additional desirable operations past just insert and search is we might have to remove something, take something out of the container because it's no longer important. Sometimes you may look at sorting the dictionary, which sounds like, well, of course you would want to sort a dictionary. But don't get too tied up in thinking about dictionary the book. Dictionary the book is just a really good analogy for what we're doing, because what we use in a dictionary is a key, which is the word, and then a value that is the definition of that word. And that's why you see in the dictionary they're in pairs. You wouldn't want the dictionary to have all of the words on one page and say, well, you got to look up banana on page 47, and then you go to page 47. Which one of these definitions is banana? I don't have the key here. So you think of a dictionary as being sorted, but that's a human artifact on the book that we use to look those words up. Imagine that you had a book dictionary and the words weren't in sorted order. How would you look up anything? You would only be able to do a linear search. Okay, I'm trying to find hammer. You look at on average, you would only have to look up half of the words in the dictionary before you found hammer. But in the worst case, you'd have to look at every single word before you found hammer. So to make that easy for the humans, we just sort these things. And then what we do when we use a book dictionary is really a binary search. Now, we don't for sure start right in the middle of the book, because we use a little bit of a smarter approach to it. We say, well, I'm looking for something in the D's. I know that the D's are already in the first half of the first half, so I'll start looking in that first quarter. But in your mind, you've already done a binary search. You've already decided, well, D is before the middle of the alphabet, and D is before the first quarter of the alphabet, and I'm going to get right in there somewhere in the middle of that around the 8th area, and that's where I'm going to crack it open to find the word that I'm looking for in the D's. If the word is after what I'm looking for, I kind of push after that. If it's before, I look in before that. But when you use the book dictionary, you're doing a binary search. And it's important that the dictionary is sorted. However, that's not part of the dictionary ADT necessarily. It may be something that you might add, but it's not necessarily required. Really, all we need is insert and search. It's really nice to have remove in case things change. After that, we start getting into things that we don't necessarily need to do, like sorting the dictionary, selecting the kth largest item in the dictionary, which of course implies some ability to sort it as well. Joining two dictionaries when I've got something that I want to combine, that's something that you have to do from time to time. And of course, the other basic operations that we do with containers, like build one, copy one, destroy one, see if it's empty, check the size, things like that. So containers with key lookup, we'll be trying to identify some container that has a fast search and a fast insert for some arbitrary key value pairs. If we just did it in sorted vectors, much like the sorted priority queue that we worked on in Project 2, the insert we know would be linear. It's already sorted. I can do a binary search, log n, to figure out where this thing goes. But then in the worst case, it goes at the very beginning, and I have to push all of those things back in a linear amount of time. On average, I'm moving about n over 2 of them, which is why I say insert an assorted vector is, of course, linear. In an unsorted vector, we have the opposite problem. It's really easy to put it in constant time, but to find it, I have to look everywhere. So that would be a linear amount of time. So if I go through a sorted or unsorted linked list, doesn't matter how you keep it in a linked list. The only way to get through a linked list is nexting it. So that means we're going to search always at a linear time. We could do our insertions at constant time, but our insertion is going to be at least linear time. And as I mentioned, we're trying to beat that linear time problem. So any one of these options, any one of these containers or implementation styles that gives us a linear component is not something that we're willing to accept. That's why we're seeing here sorted vectors problem is their insertion, whereas unsorted vectors or linked lists, their problem is their search. In a binary search tree now, we've got something that works a little differently, right? We're using that tree method where we've got 2 children left and right, and we can sort of move left for smaller things and move right for things that aren't smaller. And that gives us the heart of the STL map. On average, gives us log n search and log n insert, which is great. Worst case, of course, we could get down to a linear search or a linear insert, but that's a worst case if we build our tree fairly poorly, depending on the order that we received the data in. Average case, though, BSTs are great. They work at log n speed. The hash table, which is what we're going to be discussing today, implemented in the STL, called an unordered map, gives us average case constant time for both search and insert. That's pretty cool. Worst case, of course, we always have the worst case that we could fall back on. Maybe I just had to do a linear search. We'll look at how a worst case can show up in an unordered map. And when we talk about BSTs, we'll talk about how the worst case shows up there as well. But both of those things can't get any worse than just doing a linear search there. Big O, linear time. What if the set of keys is small? Well, what's small? Small is a fairly relative term, but something like 365 or 366 days in a leap year, that's a good set of small numbers. I can easily fit 350 of things in memory. I could fit 1,000 of things in memory without having any difficulty. Saying if I've got 1,000 different keys, I can easily look them up. So if I had those things as a constant amount or a constant numbers, I would just use a vector. Why wouldn't I just use this positionally? I can just go look up day 0, that's January 1st. I look at square bracket 0. Day 1, that's January 2nd, or sorry, index 1, and so on. So if we've got this range of integers that fits into memory, everything works out easy. It's already something that we know how to do. It's the vector. If we don't have that, now let's say I've only got 50 different things. That sounds like a small number of keys, but the value of those keys isn't fixed, right? I don't know ahead of time what each one of those 50 different things is going to be, and I just know that they come somewhere between, 0 and 2 billion. Well, I don't want to have a container that has 2 billion slots when I know that I'm only going to put 50 things in there. That's a ridiculous waste of memory. So I need to come up with some other way to figure out how to get this range of integers to fit, right? Or if I've got the situation where I've got so many integers that doesn't even fit in memory, I've got to deal with that in a different way as well. That's our brief intro into the dictionary ADT, a little bit of the reason why we're going to need it, and a little bit of how it's going to be structured when we look things up. Now let's go into the implementation here as we get at hash table fundamentals. I think the thing that I want to point out the most here, the fundamental aspect of the hash table, is that it is a table. It is a collection of data. And I've never seen a hash table that isn't implemented in contiguous memory. It's possible you can do anything any way you want. You could make a connected memory hash table. You would probably be crushing your complexity. But the hash table is this contiguous block of memory. Underneath the hash table is just a vector-like, array-like thing where if I know where to look, I can go in random access time and get there in constant amount of time and get it. That's what a hash table is. It is just a contiguous table of data. with a layer between me, the accessor, and the data in the table. That is hashing. We're going to be able to take an item and find it in the table with just having its key. We don't need all of the data, just the key. We're going to use some math on the key to turn whatever key was given to me into a table index. And that table index is just a square brackets thing that we would be using in an array or in a vector. We use the math on the key to say, okay, turn this into a table index. That's what we call the bucket. Then I can go to that bucket and find the data, hopefully, that's associated with that key. Or if I'm writing it, then that tells me where I should put it in the table. So we need these three things. We need a way to translate any key that I'm using needs to be able to be converted to an integer, because this integer is the way that I'm accessing the table. It's the square brackets thing that I use to look it up. I need compression because my translation of key into an integer is generally independent of the size of my table. I say I can convert any string into an integer. Great. Now, if I've got a table that's size 50, I can use values 0 through 49 to look things up. But if I've got a table that's size 5,000, I can use a different set of values. And I don't want my hash function to say, okay, well, here's the index you should look at, it's 79. It's like, well, I've only got a table of size 50. Index 79 is out of bounds. I'm going to go off the table with that. So compression will take whatever this gets translated from the key to an integer, make sure that it fits in the size of the current table. And lastly, because of that compression, we can often have, well, not very often, but it's possible that multiple keys, after they've been translated, after they've been compressed, because of the size of the table or maybe because of the translation function, they both think that they belong in the same location in the table, right? So if I've got a table of size 50, for instance, right, and my hash function for some key tells me it's 33, for another key it tells me it's 83. Okay, well, 33 fits in a table of size 50, 83 doesn't. I'll take a real simple compression function, I'll just modulo 50, and I'll see that 33 mod 50 is 33, and 83 mod 50 is 33. So now these two different keys think they belong in the same place. That's a collision. So collision resolution is the third portion. I mentioned we're going to be discussing that in the next lecture. But what that does is it allows two keys to be calculated to go to the same location and then still be able to find the data when we don't put two pieces of data in the same location, which we can't always do. Direct addressing is how we first look at this. And this is much like you can think of a vector. Over there, I've got my table of size t. You see values in there. You see indices on the right of that, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 items in my table. We call this table size M. So M equals 10 here. The table is named T. And on the left-hand side, I've got this blob, which is the universe of all keys. In this case, it's very simple. It's all my single-digit integers. This is just a simple way to discuss this in the slide. We don't always use integers. So we certainly aren't always limited to single digits. Inside of the universe of keys, I've got this subset of actual keys that are in the table, keys 2, 3, 5, and 8. And what I can do is look up 2, and it points me over to the table, and I just go straight to address 2. I go to index 2, and that's what we call this direct addressing. I'm taking the key and using the key to look up the value that I want directly. Over there, it looks like something that looks kind of linked listish. It could just be a pointer. However, what it is it's my bucket. My bucket has to have the key and the data. So if I were to have a collision, then I go look at some piece of data and it didn't have the key, I wouldn't know if I was looking at the right thing. Here I can tell when I go from the 2 key over to the table at index 2, and then I look at the item there. The item has the key itself, so it says, yes, you are looking at 2. And so this is not crazy. Before we've said, don't put unnecessary things in your data. So don't put a 2 as an index in your object at index 2 if the 2 indexed object is always going to be at index 2. Here, we know that because of the way the compression and collision resolution is going to work later, we might have an item whose key is not the same as its index. In direct indexing, in direct addressing, we do here, but we're keeping that there with the data as an item, key value pair. That's what's going on there. Each key here maps to an element of the array, that fundamental underlying table, that contiguous block of memory. We take a key, we go directly to that location. With hashed addressing, this is similar. You see I still have a table. It's named T. It's a little bit harder to see the indices there because they're missing, but they're the same 10 indices. So now I can say that my table is of size M. Now my universe of keys is much larger. It's so large I can't even see any of them. But inside I do have a subset of actual keys. I've got K sub 1, K sub 2, all the way through K sub 5. Those are actual keys where I have data in my table. You see that K sub 1 looks like after I apply some hash function, that's where the H of K sub 1 is. That's the hash function applied to the key K1. And that turns out it should be at index 2. And so that K1 leads me directly to that value there. K4 looks like it's at index 3. K2, once it gets hashed, goes to index 5. But because of the hash function, because of the key, or because of the size of the table, K2 and K5 are distinct. They are independent of each other, but they do hash to the same location here, and that location is index 5. So that's a collision. We'll have to deal with that later. And lastly there, we've got that K3 looking like it's peeking around somewhere around index 7 there, once we take the hash of that. So in this case, only actual keys map to an element of the array. The other things that are sort of like the dark grays over there, those are just taking up space right now. They're memory that I have allocated for my use at a later date, but for right now, they don't hold anything. So here's the first part of hashing, the hash function itself. We've got to look at some way to translate our key. And so we name this translation function T. That T takes a key and turns it into some hash int. This is an integer. So it's important that we have integers because we're going to be looking things up in arrays. So whatever the key is, we've got to find some way to translate that from key to integer. Hash function combines translation and compression. So we'll say h of the key, that's the hash of the key, is really the compression of the translation of the key. So that's the C of T of key there that gives us a table index. And we go look in the table at that place, and we can either write our data that we're writing or read our data that we're looking up. So there is a standard hash function that the standard unordered map uses. Uses it by default. So we don't have to build these things, but they're there if we need to use them. So standard hash is a thing that you want to use if you want to do your own hashing. So I think that's the way that the hash demo not the hash demo, but the lab that the hash does, the hash table lab uses standard hash. But it only provides translation here, that's important, not compression. So if you use hash, it's going to give you some integer that goes from 0 to, I think, size T max. Then you got to make sure that it fits inside your table, because your table will not be size T max. Here's our simple example. We've got this black box hash function. We got the key coming in one side from the left, and the index of where to look up or write that data on the right. In this case, we're using a very simple hash function, which is just going to be a translation. And all it does is it takes the first character of some string and returns basically the offset of that from the beginning of the alphabet. So we see return dereference C minus A there, where C is a character pointer. So dereference C gives me a character, a minus A gives me something that's 0 based if I'm talking about only lowercase characters. But over in the table at index 0 then, it makes sense why we would see a key like apple, comma 1 with the value there. Apple is the key, 1 is the value. The item itself is apple, comma 1 pair. One of the real reasons why the pair even exists in the STL is to do things just like this. The next one at index 1 is banana, of course. If I subtract A from the first letter of banana, B, I get the value 1. I go to the address 1, and there's banana with its value 3. A bunch of empty spaces there. Then in position at index 6, we see grape with its value 20. So this is how a simple translation might work. But this is to give you an idea. When the key comes in, the index comes out, and that's where we get our data from. So if banana goes in, the index 1 comes out, and we look, and that's how we can say, well, banana's value is 3. Or if I was to write banana's value into the table at that time, I would put banana and 3 there together. Or maybe I wanted to update banana. Who cares? This is how hashing works, right? So in this case, since banana is already in there, it's going to return the value 3 to me down here at the bottom. Let's talk about this translation. Translating floating point values. Sometimes your key may be a floating point value. Now, this is kind of a strange thing to do, but it could happen, right? I say it's a strange thing to do because a lot of times floating point values are approximations because of the way that the data type works. So in this case, you still may have to convert a floating point value into a key. So that means I need to take some floating point value and turn it into some integer, because all of my keys are going to be looked up with integers. So if I say the key is between 0 and 1, this is really simple to convert that to an integer. I just multiply it by m. Remember, m is my table size. So I take key multiplied by m. I take the floor of that, which gives me the integer that is not greater than the value that I got of multiplying by key and m, the highest integer not greater than that value, and I get an integer. So that's a simple way to do it when my key is between 0 and 1. I just take the floor of key times m. That is a specific way to do it when the value is between 0 and 1. This is the arbitrary way to get this done. If I've got my key between S and T, something that's not necessarily 0 and 1, then this formula gets generalized from the above version to something that looks like this. I'll take that same thing, I'm going to take some floating point number and then multiply it by the size of the table m and take the floor, right? But in this case, I'm not using the key itself because I'm trying to figure out where the key lies between S and T. So here I'll take key minus S, divide that by T minus S. So T minus S is the total width of the interval, and key minus S is how far the key is from the beginning of the interval. I divide that, that gives me some fractional version of where I might find that bucket, multiply by M, take the floor, and there's where my key should show up. It's notable that if S and T are 0 and 1, this formula turns into that formula, right? So here's an example. Try this range, 1.38 up to, but not including, 6.75. With a hash table of size 13, we've got m equals 13, 13 buckets. What I'm trying to figure out is, if my key is 3.65, where should I look in the table? Where should I put things in the table? If the table is of size 13, and I say my range of keys is 1.38 to 6.75, where does 3.65 go? And all we have to do is plug those values into this formula right above that. I've got S as 1.38, I've got T as 6.75, and I've got key as 3.65. Going through some math, we'll see the function here. Down at the bottom, I've got these 13 buckets laid out from 0 to 12. I'm going to plug things into my formula. I say H of 3.65 is equal to the floor of 3.65 minus 1.38 divided by 6.75 minus 1.38, all of that times 13. The fractions get a little simpler. It looks like I'm taking the floor of 5.495, which is just bin 5. And you'll see that on this interval from 1.38 to 6.75, 3.65 falls right about there, and that lines up. All we're doing is a mapping from floating point value to integer value. Translating integers. Well, remember, the first part of translating is to get our key to be an integer. So the easiest hash function that we could think of is integer, you're an integer, we're done. So the translation of the key is the key itself. Now that might work. It might not always work though. If I've got things like a bunch of exam grades, well, I know that some people are going to have the same score in the exam, so I don't expect I'm going to work out too well there. If I've got something like student ID numbers, well, now I've got a lot more. There's 8 digits in the unique IDs at U of M, and they give me a large number. There's nowhere near that many students in my class, so I don't want to just use that key. I don't want to use that integer as the key itself. So one other way I might do this is to use modular arithmetic. Here, I can say, I'll take that hash of the key as just the key itself, and then I'm going to compress this and say key mod m, divide by the table size, take the remainder. That tells me where to look for that particular key. This works out really good if the keys are randomly distributed, but often they're not. We talked about midterm scores. Since all the bubbles are multiples at 2.5, there's some scores you just can't get if we're just taking multiple choice grades. Another example of keys that are not randomly distributed, if you ask a whole room full of people, think of a number between 1 and 10. I don't think that 1/10 of those people would have picked 2. There are some cultural things that you pick lucky numbers or favorite numbers. Not all numbers are equally favored. So it's not great if we just take the number itself for all of our integers. If our data is randomly generated, it's good. But if it's not, then it's not the greatest. Because if it's not randomly distributed, then we end up with more collisions than necessary. And more collision resolution takes more time. We don't want to pick a bad m. Remember, m is a table size. If m and my key have common factors, when I do this division of key by m, I'm going to be looking at the same thing repeatedly. So it's important to make sure that we find a way to either get a mod m, something that's prime that would be nice, or some ways to eliminate common factors there. So we looked at translating looked at translating floating point numbers, translating integers. Let's talk really about one of the most common ways that hash tables are used with strings as keys, to be able to go look things up by string. One simple way to translate a string is just to take all the characters. They've all got a number value. They're all ASCII characters. Let's just add them all up. Every character, sum them up. There's a simple hash function. Now, we can see with the problem case here, like stop, tops, pots, and spot, all have those same 4 letters in some order or another. O, P, S, T. You could even put ops in there. But that's another word. So if I was to just add up those 4 characters, all 4 of these words would say, well, I think that we should be at this particular index. So that was going to give me more collisions. Another way to do this is to note that character position is important. Like where the character is in the string means something. And this is easily understood if you look at the value here at the bottom, 1, 2, 3, or 3, 2, 1. We know of 1, 2, 3 as 123, 3, 2, 1 is 321. They've got the same digits, but no one ever confuses the values of those two things, because we're very used to looking at the position of values in this string. This is a string of numbers now, the 1, the 2, the 3. The fact that the 1 is in that first position there means that it affects the overall value more than the others, because it's multiplied by 10 squared. The 2 is multiplied by 10 to the first, and the 3 is multiplied by 10 to the 0 or 1. So that 3 being the biggest digit in the number still affects the number the least, because its multiplier is the smallest. So if we do the same thing and say that an S at the beginning of stop is worth more to the hash int than an S at the end, as in tops, then we can see that we can start to figure out how we can look at these same 4 letters but still come up with different values, because the S at the end of tops and the S at the end of pots both contribute the same, but the T in stop and the T in tops contribute differently. So we can expect a different value from most of the time when we do our strings. We have strings with the same characters because they're in a different order, that this positioning thing is going to make them different. So in the case of digits, of course, we multiply by 10 in every position because there's only 10 digits. We might want to multiply by 26 because there's 26 different values. If I'm talking about lowercase letters, if I want to use uppercase ASCII or additional characters and whatnot, then I've got to find some bigger multiplier to make sure that I can say that every place is independent of another. That's how we make sure that a 5 doesn't contribute because it's in the wrong place here. We say, well, the 5 is one option out of 10. If I multiply that whole thing by 10, I'll be sure to move past any effect that this 5 can have on a previous position. So this is a better way to translate. This is what's known as the Ravine fingerprint. And in the Ravine fingerprint, we're going to take some character, its ASCII code, and then multiply by some value, and then add the next character. Just like we do when we get to 123. I take 1, I multiply it by 10, I add 2, I multiply that by 10, I add 3, that's 123. So in the Ravine fingerprint, we've got this set of characters here, Tom, Marvolo, Riddle. But all we can see is these first 5 of them. T, O, M, space, M. So even spaces are part of the string, so I need to take care of their ASCII contribution as well. So that's a hex 20 or 32 there. You see that space there. But as I take this running fingerprint, I start with a T, and I just add that 84. Then I multiply that by 10, and I'm using 10 here because I've got 10 fingers, and I'm used to multiplying by 10, just to make this easy to see. Later on, when we do this for real, we're not going to use 10 because 10 doesn't help me clear past all of my possible values. Right? I don't know if I'm adding an 8 times 10 plus 4 or just 84. I could have a character that was an 8 followed by a character that was a 4 if I was using that multiply by 10s, and that would be the same as having one character whose value was 84. And so we wouldn't use the 10 there. We need something bigger to make sure that we don't have multiple characters influencing what could look like a single character. So we take the O, we multiply the T by 10, and then add the 79. Then we take the TO, multiply that by 10, and add 77 for the M. Then we take that quantity, multiply it by 10 again. That's my running fingerprint, right? Multiply by 10, I add to the 32. What happens then is, if I shuffle these characters, I usually change the result. So I am Lord Voldemort would give me a completely different fingerprint, even though it has the exact same characters as Tom Marvolo Riddle. Compression. This is where we take the hash int and make sure that it ends up in the range of 0 up to but not including M. So the hash int, depending on how it gets calculated, may be something that actually ends up less than 0, or it might be greater than or equal to M. So we need to make sure that when I take that value and square brackets it, I don't go out of my memory segment. That's where compression comes in. The simplest way to do it, of course, is some more modular arithmetic. Let's take the absolute value of that hash int, mod it by M. If M is some prime number, then I've eliminated this common factors thing because M doesn't have any common factors other than itself and 1. So there won't be any common factors between hash int and M if I choose a prime number. So that's a good way to do it. Sometimes, however, I won't have control of the table and I can't necessarily make sure that my M is prime, so I can use this multiply and divide method. Here, I'm going to take this hash int and multiply it by some other integer a and then add b to it and choose a couple of different primes. So maybe I can't choose the size of the table M as being a prime, but I can make sure that I can pick a and b as prime, and I would try to make sure that this would then make sure that I don't have common factors between my key, which is a times hash int plus b. That's not my key, but that's my my calculation, my translation. A times the hash int plus b now gives me something that cannot have a common factor with mod M if I'm able to choose those two prime numbers, even if I can't choose my table size to be a prime number. I just want to make sure that a mod M does not equal 0, because that would be problematical, right? Because I'm multiplying by a and then I'm dividing by some factor of a, and it ends up problematical. So we'll make sure that a in mod M does not equal 0, and we can compress anything we want with either just straight division or with multiply and divide. That was the hash function. The compression now, we'll talk about that just a little bit. Remember that the hash function itself really, we talked about the translation. So the hash function itself is really the hashing of the key which is the compression of the translation of the key. And that gives us a table index. I go look things up. So previously, I had my black box that looked like this. I've got the key coming in, the black box hash function, index coming out, and it was just simple translate by taking that first character, subtracting A from it, and going to that location. So lemon goes in this case. The index comes out as 11 because I can subtract A from L, and that gives me 11. But my table of size 8 now has indices only running from 0 to 7. If I try to hit that, I have gone off the bottom of my table. This is where I need compression. Hash table size, M, is about the number of elements expected. Of course, if we're not sure, we want to make sure we have enough room, so we guess high. But we do like to keep it as close as we can to the data size when possible, because it saves us space. What we need to be able to do is return my keys as integers in that range. That's what the hash table function does. So the size of the table is vitally important to the overall hash function. It's not important to the translation, but it is important to the compression and how I get my ultimate table address out. So in this case, we've added a compression function down here below translate. And all that does is just take the incoming integer, which is my hash int I, and mod that by the table size. So in this case, if I were to stick in lemon now, lemon comes out mod by my table size 8, 11 was the index, or sorry, the hash int 11 divided by 8 is 1 remainder 3. I use the remainder 3 to go say, let's look for or write lemon in the table at index 3. And now we've got a chance to do this. So we can see how we could put something like mango in there. We can see that shows up because of collision resolution there, or not because of compression. Mango shows up at index 4. Pear now shows up at index 7. So this allows us to see how it's important that the key is also with the item. Because if I said, well, I'm looking for, I always come to the, say I'm looking for dragon fruit. Say, well, dragon fruit, that should be at index 3. Go get it. If I went there and just pulled out that 2 value, I wouldn't realize that I don't have the dragon fruit value. I've got the lemon value. So this is why it's important to have the key, because now the key is not necessarily always going to be at a fixed location, right? If I had put dragon fruit in there first, obviously lemon couldn't go in there. I'd have to find some way to deal with that collision. We'll talk about that later, but sometimes, depending on the order that I insert things in, I might put something where it originally belongs, where it originally hashed to. Sometimes I may move it along a little bit because we have collisions. Orange comes in, I put a 6 on there. Oh, collision. Okay, so orange hashes to 6. After I translate it and compress it, it tells me go to index 6 and write orange there. But when I get there, grape and 20 are there, and this is why we do need collision resolution. We'll talk about that in the next lecture. Our summary here for the hash table then is we're looking for this efficient abstract data type for insert, search, and probably remove. Hashing is what takes a key and turns it into a table index. We do this in a couple of steps. First, we translate the key to an integer. We call that the hash int, or the T of the key, the translation of the key. Then we compress that hash int, which takes it and makes sure that it fits into the range of 0 up to, but not including, M, my current table size. So the compression of the hash int gives me my table index. So H of key is the same as C of T of key. The hash of the key is the compression of the translation of the key. Those are our hash table fundamentals. Let's do a little bit of analysis and application here. We'll get some ideas about why this works the way that it does and how we can use them on a regular basis. We had one semester where the staff members of EECS 281 in a staff meeting, every one of them had an interview question that relied upon using hash tables. Don't know why hash tables aren't that great. They're the best thing since forever, but they seem to get a lot of use. It's useful because the way that the hash table is often used is it's a much more direct step between your thought process and the data. right? So it's a little bit more indirect if I have to do a linear search to look something up, or if I had to do some linear tabulation of something. I've got this direct thing to do it. So I think that's why hash table questions often come up. It's not because hash tables are so awesome. It's not because anybody ever writes a hash table, but because it does a straight translation of how you think to data, it allows those questions to be a little bit more instructive on what your thought process is like. What is a good hash function? Of course, we were using these hash functions to get at our data. The benefits of the hash table, as we saw, we said that in average case, it was constant time, but in the worst case, it would be linear. What would cause that worst case? Well, it turns out a bad hash function or some bad data would really cause that. If I've got a good hash function, and a good hash function has got some things to do here, right? It's got to be easy to compute, has to work for every key. We can't say, well, we take every string, but any string that starts with Z, this just breaks. So it has to be able to take anything in the range of keys and convert that. And it also has to be repeatable. So if I give it banana and then I hash it again later, it still gives me the same value, because I want to be able to write it into a definitive place and then come back and look it up deterministically, because I can use that same hash to get the same value for the same key over and over again. We would like for our hash function to distribute the keys evenly in the table. When I don't have collisions, my hash tables work faster. If I'm trying to hash everything by their, everyone in the class by their grade, we're going to see a big bell curve where a lot of people are going to be colliding at some median or sort of value where the center of this bell curve is. So I can come up with a really poor hash function, this trivial one here that says h of key is just return 0. That does this stuff. It's easy to compute. It always computes a hash for whatever key I give it, because it just returns 0. And every time I use it, it always gives me the same value for that particular key, because it always gives me the same value for every key. So it's almost good. However, it does not distribute the keys evenly in the table. It makes every key collide, in fact. So it maximizes collisions. It's easy to compute, but poor distribution. So if we could assume perfect hashing, because we haven't talked about collision resolution yet, imagine that every time I do a hash of some key and I go to that location of the table, I've got the value that I was looking for, or I've got an empty space because I'm writing it in there. What happens to my costs? If I say insertion costs and search costs and removal costs is all constant time, because I can get there right away, and constant time is the kind of thing that brings you joy. That's fast. It would be nice to live in the perfect world if we always had perfect hashing. Some things do perfect hashing. The way that the compiler uses all of the identifiers in your code, function names, variable names, and such, it does a perfect hashing there to make that work. And it does it by using multiple passes. So you can get a perfect hashing function, but you do need to have a situation where before you start writing a hash function, you know all of the possible keys that would be used. So where are real-world hash tables used? Of course, we've already discussed this. We've talked about the unordered set. We've talked about the unordered map. There's also the unordered set, where now it's just the key. We don't have the item as the key value pair, it's just the key. So this is useful when we really just need to know set membership. The map is the one that uses the value with it. It turns out that the unordered map is just an adapter of the unordered set. We always can go look up something by key. That's what the unordered set does. The unordered map says, oh, by the way, when you go look up that key, there's a pair there now, so the data is included as well. So underneath the unordered map is really an unordered set. We have unordered multi-set and unordered multi-map. Those are things that look like they give me the ability to have more than one value at a particular key. So I've got a bunch of different cars, for instance. We're talking about a car project here. If I might say, here's my Chevrolets, and that's my key, and that key says, well, there's 14 Chevrolets on the lot. I need some way to say, well, all of these things actually respond to Chevrolet. If someone's here, they're trying to buy a Chevy, I need to look that up. They're looking for a Ford Focus, maybe I say, well, here's my collection of Ford Foci. That was fun. Database indices are, of course, built on hash tables, something you'll be doing in this next project, SillyQL. Compilers use a hash table for identifiers. I mentioned that as well. So yes, unordered set and unordered map are both implementations of a hash table. The unordered set just has the key in it. The unordered map has the key value as a pair so that you can associate data along with the key. So here's a sample program which has the thing that Dr. P and I most want you to understand. I was trying to think of ways to tell you outrageous lies so that you would not get this wrong. Like if you do this, your hand is going to fall off. Or small bad things will happen to big people everywhere if you do this wrongly. So he talked me down. He talked me down out of just telling you outrageous lies. But I want you to pay attention now. All right. So in this sample program, it covers a couple of slides. We've included IOStream, string, and unordered map. So the IOStream and string are just for printing things out and using those as keys. The unordered map is what makes things happen here. And that gives me this templated type unordered map, of which I declare a variable here in line 7, unordered map, which maps from string, that's my key type, to value type int. So I've got the ability to look up integers by putting strings into my unordered map as keys. And this one is called months. So you see it's there, it's called months. Now listen, this is the important part. I can write something like this, line 11 here, months, square brackets, January, in a string. I would be thinking of square brackets as a place where I might put an integer. If I do this, I can write to that location, no problem. Months, square bracket, January equals 31. I didn't have to declare January. I didn't have to ask if January exists. Using square brackets causes the thing to exist. If you've got a map of string to vector, if I go say, what's at this string, you will get a vector. If there was no vector there before, there will be a new empty vector for you. But when I use square brackets, it will cause the thing to exist. And that is okay when I'm writing it in there. And this is the part where I argued with the Dr. P. I said, they're going to hear that first part. If I use square brackets, it's okay. And that's all they hear. There's more to it than that. I can use it, and it's okay when I want to write. If I'm going to write there, using square brackets always sets it up for write. And that's what these lines here, 11 through 22, do. They set up all of the months of the year and put their length in days in them. January is 31, February 28, March 31, and so on. So this creates the thing. That's great. Now what I'm probably going to do is use these strings. I'll say, hey user, what day do you, what month do you want to know about? They type in April, and I'm going to say 30. That's my plan as the programmer. We know what users can do. So here we are. Enter a month name. They type in the month name. We read it in, and then I would like to go look it up. So I could use square brackets. But remember, I said if the thing is not there when you use the square brackets, it makes something be there. It causes it to exist. Now, if I was just looking up the month named Marshmallow, it's going to say, oh yeah, that's in here. It's got a 0 in it because you use square brackets and I will cause it to exist. Months, square bracket, Marshmallow, hey, it's equal to 0. It's going to do some base initialization there. So you're going to get 0-based stuff. If you're calling that on some objects, it's going to call the default constructor, what have you. So if the user up here enters some faulty month name or just even spells it wrong, if I were to say, well, let's look up in this line here that's commented out, line 28, cout month, which is what they entered, has months, square bracket, month days. Well, if I put Marshmallow in there, it's going to say Marshmallow has 0 days, which is completely nonsensical. But it's because that using that thing in square brackets always makes it exist. It's okay when we want to write to it, or if we want to read to it and we are certain that the value is in there. So if I gave the user some menu, for instance, pick from one of these 12 months, and then they picked the one that was March, so I knew I could control the string, I know that March was in there, I would just use square brackets. But if they've got control of the input, you need to use find. That's line 31, use find. If you're not sure it's there, you have to use find. Because if it's not there and you use square brackets, it will be there. Because square brackets creates it. So, use find if you don't know that it's there. So, if I go look for marshmallow here, this iterator is going to return me something that looks like month's end. And so, when I say, well, if the iterator is equal to month's end, then the month that you gave me is not really a month. That wasn't found. So I'm going to just print out that month not found. Otherwise, if it is in there, this iterator that gets returned is an iterator that's pointing to the item, which is just a pair, the key and the value. So I can say cout iterator first, that's the key. So if I put in March, then it would say March has 30 days, no, 31 days, right? Yeah, 31 days in March. So its second is the value. So this iterator, if it finds the thing, is pointing at the item. If it doesn't find the thing, it's pointing past the end of all the data. So this helps me from printing nonsensical things, like marshmallow has 0 days. That's it. This is the time where you should rewind and go back and listen to all this ranting and raving and shouting and all of the outrageous lies. Make sure that you understand. Don't use square brackets when you need to use find. Conversely, don't use find when square brackets works, but know what the difference is. Some major uses of hash tables: sets of integers, strings, images, class objects. We can use that to check set membership. We can use it to detect or filter duplicates. This is great. As I look at all of the things that I have there, you can use it to find unique elements or find matching elements. That's one that happens pretty regularly. I can look for instance, if I'm looking for pairs of numbers that sum to 0, I can say, well, if I've got A, I'm going to square brackets and write that into the hash table. Then when I get B, I'm going to take the opposite of B and then try to use that as square brackets to go look the thing up. If it's there, then I've found a matching pair. It's a pretty common application there. Sometimes when we use key value storage, and I really need to get those values in there for counting things, much like you may have done if you had used it's possible to have used an unordered map for question 26 on the midterm. But we won't talk about that because we haven't talked about this before the midterm. So it's possible to use to completely get a perfect score without using an unordered map. So that's the kind of thing that would be done there. I don't want to get into giving anything away, so there's still a couple of people to take the exam here. Maintaining sparse vectors. Now this is a situation where I said something earlier. I said, well, maybe I've got 50 students in my course, and each one of them has a unique ID that has these 10 to the 8th different values that I can use. I don't want to have a vector of size 10 to the 8. I just want to have a vector of size 50 and then know how to look people's data up in there. Maintain link structures where I've got a key type is equal to the value type, so you can do some pretty interesting things that way too. How about sorting a hash table? Here's our example that we had with our hash table containing apple, banana, a space, no, lemon, mango, another space, grape, and pear. So if I wanted to sort a hash table, what does that mean? Do I sort the keys? Am I sorting the values? If I do that, it doesn't look like I can do it in place, because later on when I go to look up lemon, if I've moved it to its alphabetical location, things aren't going to be where I thought they were going to be. So sorting a hash table is not generally a good thing. We know that hashing is an efficient way to do insert, search, and remove, but hashing leads to inefficient storage if I'm going to try to sort the items in the dictionary, or to select some kth largest, because that implies I needed some sort to figure out where the kth largest item is. So this is something that I want to be aware of. as I mentioned, the difference between a dictionary ADT and a dictionary the human book. How about a book index, like an actual book? Now we're back to books, not necessarily a dictionary. We don't have an index in a dictionary, but a textbook on, say, data structures and algorithms. How would I look up something like hash table or complexity or any one of those things you look? So one way to do it is I can go through the table of contents, and that gives me a rough idea where I can go to that chapter and then start paging around. But the index is a way to do that. I say this example of an index over there says if I wanted to know about Aristotle in this book, I go look in the index. It says Aristotle is first discussed on page 150. So with really quick time, I'm doing this short search of the index that gives me direct access to something. So this is kind of like a hash table, right? I've got this thing where I've got these things I can look up and go directly to their page. How would you construct an index? That's something you can think about. That would be applicable here as we look at project 3. Composite hash functions are a thing here. What happens if I've got sort of more than one key? So for instance, if I was to use last names or names from students in class, I might say, well, I could just use the last name, but we know that there's more than one person in the class with some last names. There's duplicates there, and so that would not be good for me if I did that. So I might do this thing where I've got a composite hash function where I use the last name and the first name and combine those two things to use them as a key. So the example here with this Pokemon, we've got somebody using a latitude and a longitude as a pair of items to say, now I can use this as a hash for our geolocation. So how do we combine hash functions? Well, one way to do it is to kind of use that previous way that we talked about in the Ravine Fingerprint. I can take the hash of one position, then I'll take the hash of the other value in the key and then multiply that by some p, right? And then if I mod that by m, I've got something back in there. How do we hash class objects? That's another good question. Well, we could do that by taking some value out of them. So these are just things to think about as you try to figure out how to do hashing. We have the question, is h, where the hash of one item in the, so one portion of the key plus p times another portion of the key, is that a good way to combine hash functions? Well, it's fast to compute. Remember that a good hash function is fast to compute, evenly distributes values, and has no easily predictable collisions. If we were to continue using this mechanism here where it's h1 plus p times h2, and then I've added a p times h3 if I'm trying to do 3 of these combinations here, we see that it's hard to distinguish whether the h3 and the h2, how their contribution is distinguished because they're multiplied by the same value. Of course, we could do something Ravine Fingerprint-like and multiply by some value multiple times. So I've got like a p to the first power times h2, a p to the second power times h3. But with wildly different types, you may have a first name and a phone number, or a last name and a city. You don't necessarily know how to get those p's chosen. It's really easy when I'm talking about 10 digits. I pick a 10, that p is going to multiply and make sure that there's no predictable collision between p times h2 and p times h3. So one other way that this might often get done is to use something that combines multiple values here. So here we've got this seed and we've got this XOR equals. We're going to take this bitwise XORing thing and then change seed by taking h1 and adding some constant value there. So this is something that helps us with some primary number there. And then the stuff that goes on to the rest of it, they've taken the seed and shifted it to the left. That's not a read now, like a C in or C out. Shifted it, bitwise shifted it to the left 6, and bitwise shifted it to the right 2. Add those things together. So this, when applied repeatedly for each one of those n values, is going to give me something that has no easily predictable collisions based on multiple values being, so multiple portions of a key being combined to make a multi-item key. When do we not use hash tables? Well, there's a reason why we haven't just talked about hash tables all our lives. They are not the magic solution to everything. So there's got to be some situations where using an unordered set or an unordered map would not be good. For one, they do have a significant space overhead. We do have, remember we said we wanted it to be about M if we knew what it was ahead of time, and if we didn't know, we would guess large. So we're always going to be expecting that this has more space than we want. As we get about talking about collision resolution, we'll see that knowing the timing of this, to keep this at a time frame we like, to keep this closer to our average case, best case constant time, we can do that by having more speed. So there's a significant space overhead when I start nesting these things as well. It also does go a little bit slower because I have to do the translation compression math every time I do something. And since we do have to deal with collisions, we can end up with a situation where it is worst case. So depending on particular implementation. So beware of that. When the keys are small ints, we should just use bucket arrays. Over there we see a picture of cute kitties in buckets. Who would put a kitty in a bucket? I don't know. But I can tell you that no kittens were harmed in the filming of this video. All right, some keys can be coerced to small integers, like enums or simple fractions or months or something like that. So why have, I mean, our example with January, February, March as our keys was great, but those months, I know those ahead of time. If I was gonna offer them to the user as some menued thing, I wouldn't even really read that in as March. I'd just read it as the index of March. That's how I would get it. So that's because I've got the keys as a small set of integers. If I've got static data, my data isn't changing quite often, and maybe I'm just doing sort of a bunch of lookups on a regular basis. One way I could do it is say, well, if the data is not going to change, I might just sort it. And then I've got the smallest footprint I could use, sort it once, I do the work, and then I got a whole bunch of quick binary searches. I mean, they're not constant time quick, but they're logarithmic time, and that's oftentimes quite good enough. And then another reason why I would not use a hash table is if I've got a whole bunch of data, and every time I use it, I use all of it. So for instance, I wouldn't want to use a hash table to look up my paychecks when I'm printing paychecks for an HR firm, because I don't just pick a person to write their paycheck. When it comes pay time, I pay all of them. So there's no need to have this easy way to look up someone by name in that particular situation. That's hash table analysis and application, and we've seen how hash tables work a bit, and we've seen when and why we would use them. Up next, we're going to check out this word count demo, and it's going to take me a fraction of a second here to get things going well, but during that time, why don't you go and download this code here. So there's a link there, bit.ly.eecs281 word count demo, and I am going to do this thing as well. So let me get a new window here. That's the good one. All right. Sorry about this. Get the keyboard up. That's good. All right. Where's the one that I'm looking for? That's the one I want. Okay, there's my Kane terminal, and that's the one I want. All right, so let's check this word count demo out, and we're gonna give it a run, see. All right, so from my, I'm gonna send myself over to Kane here. Oh, wait, that's not right. Hold on 1 second. That'll do it. There we go. Duo. Where's my phone? I have no phone. Why would that happen? All right. We have the phone. We can do it now. Approve. Sorry, bear with me here. Passcode. Let's go. One. Send it again. Approve. All right, and we're in. Okay. Bring our keyboard back, and you can see what's going on. And am I on my MacBook? I'm on my MacBook. What will that do now? Approve. All right, there we are in Kane. So, make a demo directory and change into that. Then I'm going to, at the command line, wget bit.ly x281-word count demo. I'll put that into word count.cpp. We've got it. Great. If I do an ls, there's word count.cpp. What I want to do is take a quick look at that code. There it is. It's rainbow colored here. That's what I've got in my terminal going on here. Let's just take a quick perusal of what's there. I can swipe all the way down to the bottom here. And it looks like there's about 100 lines of code here. Plenty of comments. We've got some display count 10. That's what we're going to do is take some file and look at all of the words in that file and use this hash table to, every time I see a word, I'm going to increment the number of times I've seen that word. So I've got this word count pair. So I'm going to be taking a pair from the string to the number of times I've seen it, an integer here. In this case, we're going to use a size t. So that's my word count pair is really just a pair of string, comma, unsigned integer. I've got count sort now, which is going to allow me to do some sorting later on. And I've got this cleanup, which takes any word that's given to me in the text and removes punctuation, makes it lowercase, so that I just get the characters that are actual text words. So that's what this one does. It goes through it and says that there's punctuation. Let's erase that. and so on. It takes anything and makes it lowercase so that all of these things work out. That's what cleanup does. Then all of the interesting part here is in my main. See, I've got enter some file name. I give it a file name. It goes to look for the file name. It opens the file name. If it can open the file name, life is good. Then as long as it can read files from it, read from that file, it cleans up each word. If the word is a non-zero length after being cleaned up, then it uses this plus counts square brackets word. That is the unordered map use. You see there in line 54, it's declared unordered map from string to size t named counts. So when I put word in square brackets there, that's because I want to update the number of counts here. And this is okay that I haven't used find, because I know I want to make changes to counts at that location. Even the very first time when I use that word in there and it doesn't exist already, using square brackets makes it exist and gives it the value 0. Then I plus it, and things are exactly as I would expect them to be. It didn't exist before this word, and now after this word is passed, it's got a value 1 in there. So it's okay to use square brackets here, but that's because I know that I'm glad to make those changes. When this is not going to be good, if you're looking up something that doesn't exist, it makes the thing exist. So if I have you look up 100,000 things in the table and all of them are misses, your table size is just grown by 100,000 if you're using square brackets when you should be using find, because you don't know if it's there yet. If you do know it's there, use it. All right, now the rest of this, it needs to do some sorting, and we said that dictionaries are not good for that. The dictionary ADT is not good for that. The hash table unordered map is not good for that. It is unordered. So saying that we're going to sort it is not a good thing. The only way we can get this done is if we go through here and check the size of counts in line 83. I'm going to make myself something that I can put those things in, and I will sort them here. I'm going to take those items from the hash table and stick them into sortable and sort them. So I'm going to have to make a full copy of all the data in my hash table to get this sorted, which is why we say the hash table is not great for sorting. After a sort, then we're just going to use a count sort here, which is going to be giving me some descending sort so that I can look at things from big to small, and I can print the top 10 of them. And that's what this does here. All right, so that's the code. It says that I can say a G++ minus standard equals C++1Z, and I'm going to take word count.cpp minus O into word count. It compiles. Life is good. I run word count. It says, give me a file name. How about word count.cpp? We see the most often used word is the. Not surprising, there's some English language comments in the file. So the shows up 11 times, word shows up 9 times, include I, to, we got some size T. You see the cleanup there has removed the underscore in size T. But this is what the word count demo does. So if you've got some interest in how to use this, this is a good little piece of code to play around with. It gives you a chance to declare and use a hash table. All right. That is the end of the slides here. What's going on there? Just checking my chats here. They're talking SSH. Oh yeah. Yeah, I'm a shortcut user. Yeah, it's in a .ssh config file. Let's see something else that's cool. I can log out of Kane like that. I'm on my local machine here, and then I can go back into Kane with no 2FA. Yeah. All right. That is in the EECS280.org stuff. There's some stuff in there about it. If you need some help about it, we will be able to discuss it in office hours. All right, so that's about lunchtime. I think we've covered our slides, we've covered our demo. that's what it looks like.